In this section, I'm going to be talking about k-nearest neighbors, kNN. The principle behind nearest neighbor methods is to find a predefined number of training samples closest in distance to the new point and predict the label from these. For more information, please visit scikit-learn.org to learn more about nearest neighbors with some examples. As a summary, kNN relies only on the distance between observations. It is very easy to determine the distance in two dimensions. If you recall, the Pythagorean theorem can be applied to find the Euclidean distance between two observations, each with two features. And the formula, if you recall, distance equals square root of x2 minus x1 to the power of 2 plus y2 minus y1 to the power of 2. And of course, the generalized Euclidean distance between observations would be the square root of x1 minus y1 to the power of 2 plus x2 minus y2 to the power of 2 plus dot 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 x sub n minus y sub n all to the power of 2. In the next section, I want to talk about the pros and cons of using the kNN algorithm. First, it is extremely easy to implement. Second, it is a lazy learning algorithm. Therefore, it requires no training prior to making real-time predictions. This distinguishes the kNN algorithm, making it faster than other algorithms that require training, such as linear regression or SVM. Because the algorithm requires no training before making the predictions, new data can be added seamlessly. When it comes to the cons, the kNN algorithm doesn't work well with high dimensional data because with large number of dimensions, it becomes difficult for the algorithm to calculate the distance in each dimension. Also, the kNN algorithm has a high prediction cost for large data sets. This is because large data sets have a high cost of calculating distance between a new point and each existing point. Finally, as a third point, the kNN algorithm doesn't work well with categorical features, since it is difficult to find the distance between dimensions with categorical features. When it comes to use cases, neighbor-based methods are also known as non-generalizing machine learning methods and have become very successful in a large number of classification and regression problems, such as handwritten digits or satellite image scenes. Why? Well, because it is a non-parametric method, aka non-generalizing machine learning method. It has been incredibly successful in classification situations where you have a decision boundary that is very irregular. Below is an example that shows implementation of kNN on iris dataset. This iris dataset has 50 samples for each different species of the iris flower, which totals 150. For each sample, you have the sepal length and sepal width, the petal length, the petal width, and a species name with a class and label. So in this case, a kNN model was built to classify the species based on the sepal length and width measurements. Now this nearest neighbors classification uses the uniform weights, which is a value assigned to a query point computed from a simple majority vote of the nearest neighbors. And as you can see here, it fit pretty nicely as far as Setosa, versicolor, and virginica. So again, when the weights is uniform, it assigns uniform weights to each neighbor. Now on the other hand, if the weights is a distance, then the weights are assigned proportionally to the inverse of the distance from the query point. I wanted to mention k equals 15 over here. It was found for this model that for a k value between the range of 3 to 19, the model accuracy was 96.6%. So as you can see here, there are some instances where there was incorrect classification. But for the most part, the model was 96.6% accurate in this case. So first thing I'm going to do is load some modules and import some data to play with from the database. I'm going to illustrate how the algorithm works with an example. So I'm going to be using a data set from Kaggle, and here's the following link to it. This data set is from Pima Indian's diabetes database, predicting the onset of diabetes based on diagnostic measures. The dataset is originally from the National Institute of Diabetes and Digestive and Kidney Diseases. So we're going to download the dataset and look at several predictor variables and one target variable. So I'm going to go ahead and copy and paste some code. Going to go ahead and run it. And you can see the first 5 records with our predictor variables and our target variable called outcome. So we have age, diabetes pedigree function, BMI, insulin, skin thickness, blood pressure, glucose, and pregnancies. If we wanted to build a correlation matrix, I'm going to go ahead and copy and paste some code. And right off the bat, you can see how the predictor variables tie with the target variable. So in this case, glucose, BMI, age, pregnancies have a weak to moderate positive correlation. So I'm going to go ahead and copy and paste some code to create a heat map that will show the correlation of attributes with class variables. So essentially it's the same values, but shown in a heat map. And as you can see, there is a positive correlation between skin thickness and insulin, or glucose and insulin, or glucose and your target variable, which is 1 if a patient has diabetes and 0 if a patient does not have diabetes. So 2 predictor variables that I'm going to be taking a closer look at are the BMI and glucose variables. Since they, as you can see here, they have the highest positive correlation with the target variable. So I'm going to try to build a 2-class classification using the kNN algorithm and show their associated decision boundaries. So I'm going to go ahead and copy and paste some code, which is pretty lengthy, but again, I'm going to be looking at glucose, BMI. I'm going to start with a kNN value of 10. I'm going to be subsetting the data containing the labels, creating a color map, creating an instance of neighbor classifier and fit the data, with the weights being uniform and weights proportional to the inverse of the distance from the query point. So first I'm going to initialize and run the classifier, create the decision boundaries so that it looks nice on a plot, predict where the boundaries are at, create a color plot, and plot all my training points. And in this case, the first example, there's going to be no split between training or testing points. So in this case, I'm going to be plotting all the points. So I'm going to go ahead and run. And the plots are generated. So the first plot over here is based off of the weights being uniform. And the second plot is weights based being proportional to the inverse of the distance from the query point. Now you can see here, it did a nice job with the boundaries. But if we look at the distance, it did a little bit of a better job here. Now again, our k value is 10, whereby the choice of k can dramatically affect the results of the kNN model. Of course, I selected k being 10, but if I selected a smaller k, it would have yielded a more detailed model, running into the risk of overfitting. And of course, if I increase the value of k, it would reduce the noise and it would yield smoother boundaries, but of course running into the risk of underfitting, whereby you're simply predicting the majority class. So a good approach typically is to choose the k with the lowest error rate. And of course, the rule of thumb is to pick a range of k near the square root of the training set size. Now, from the following plot of glucose and BMI, a data miner might conclude that these features produce a good model to classify whether an individual has diabetes based on these diagnostic measurements that are in the data set. As you can see, for the most part, based on the K value, it seemed like it did a pretty good job. So in the next step, what I'm gonna go ahead and do is split the diabetes data set into 2/3 training set and a third test set to perform the kNN on the test set to classify the instances whether or not a patient has diabetes, and also be able to measure the classifier's exactness and completeness by comparing the error rate with the K value. Now, before I do, I'm going to copy and paste some code to take a look at the box plot of glucose versus outcome. And as you can see here, glucose does play a role in whether a person does or does not have diabetes. So I'm going to also try to create a box plot for my BMI versus outcome. And sure enough, as can be seen here, BMI also does play a role. When it comes to these values, they can be categorized as shown on the screen. And this is directly from nih.gov, whereby a value of less than 18.5 is underweight, between 18.5 to 25 normal weight, overweight is between 25 to 29.9, and obese any BMI value of 30 or above. So I'm going to go ahead also and copy and paste some code to generate a pair plot. And sure enough, the predictor variables BMI and glucose do play a role in the outcome. So the higher the value of BMI and glucose, the more likely the person has diabetes. This is fascinating. And again, if you recall, one over here, a value of 1 is your outcome. And as a quick reminder, this data set is from patients that are all females, at least 21 years of age, of Pima Indian heritage. Now, reverting back to our kNN model predictions, I'm going to, again, copy and paste some code that splits my diabetes data into 2/3 training set and a third test set. And I'm going to be able to perform kNN on the test set to classify instances by whether or not a patient has diabetes or not. So I'm going to go ahead and copy and paste some code. Just going to go through it really quick. I'm going now to select a kNN value of 25. You've seen all of this before. I'm going to split my data set, whereby a third of my data set is going to be a test set and 2/3 is going to be my training set over here. I'm going to initialize and run the classifier, plot my boundaries, create a color plot, run my classifier, and then generate a scatter plot of all my test data points. So I'm going to go ahead and run it. And as you can see from below, I have two plots of my BMI versus glucose. And as you can see here from the boundaries, my kNN model prediction did very well in its classification, whether a patient has diabetes or not, based on my diagnostic measurements. And as you can see here in the first plot, my nearest neighbor's classification used the uniform weights, and below it used my weights as distance, which are proportional to the inverse of the distance from the query point. This is truly fascinating. So we were able to, again, split our diabetes data set, whereby 2/3 is used for training and 1/3 is used for testing. We performed a kNN on the test set, and we're able to classify the instances by whether or not a patient has diabetes. In the next section, we're going to be talking about the confusion matrix for the kNN algorithm that is actually performed on this data, and be able to determine its precision, which is the classifier's exactness, and its recall, which is the classifier's completeness, and its accuracy. Truly fascinating. This completes our section on kNN model predictions.